So thank you very much for coming this morning. It's an honor to speak here in front of you on this result of oracle separation of BQP in the polynomial hierarchy. This is joint work with Raz. Okay, so I will start with recalling some of the favorite and most well-known complexity classes. So let's start with P, things that we can compute in polynomial times. This is what we consider as things that we can compute efficiently on a classical device. NP is the class of things that we can verify efficiently once we are handed a solution. QIP is the class of things that we can refute efficiently or check that there is no solution. Or in other words, we can check that all possible assignments are false. Right? So basically, NP corresponds to whether there exists some witness, and QIP whether for all witnesses some property holds. And we can take these quantifiers, their existence for all, we can use several of them, alternating between the two. And this gives us the power of the polynomial hierarchy. Okay, so basically, this is an infinite hierarchy of classes, one that's specified for each number of quantifiers. And this entire polynomial hierarchy sits inside what we call P-space, things that we can compute in polynomial space. Okay, we can also talk about randomized algorithm. In randomized algorithm, we want to get the answer right with 99% probability, let's say. And we want to run in polynomial time and get the answer correct with 99% probability for each input. So we call this class BPP. And one of the first famous examples was the fact that you can check whether a number is prime or not using randomized algorithm. This is a Miller-Rabin algorithm. And it took something like 30 years to come up with a deterministic algorithm for this task. And by now we believe that actually P equals BPP, that everything that we can do in a randomized algorithm, any decision task, can also be done in a deterministic algorithm. But currently we still don't know it. So we know that BPP is inside this polynomial hierarchy. Okay, so really the motivating question for this talk is where does BQP, where does quantum polynomial time sits inside this picture, okay? So BQP stands for bounded error, quantum polynomial time, or things that a quantum computer can compute efficiently. And we know two things. So we know that anything that a randomized algorithm can do, also a quantum algorithm can do. So this means that BQP is bigger than BPP, or at least as big as BPP. On the other hand, we know that you can simulate a quantum algorithm on a P-space machine. So you can simulate it using polynomial space. So this means that BQP is somewhere in the middle of this picture between BPP and P-space. But we want to understand what is relation with NP, with PH, and other classes. Okay. Okay, so this is what we know. As I said, BQP is between BPP and P-space. And we want to understand whether or not BQP is inside NP or vice versa, whether BQP is inside PH or vice versa. So here I should say that I wrote a common belief, but actually it's not clear how common it is, but let's say a belief is that all these containments are false, that all these classes are incomparable, that NP and BQP are incomparable, and that PH and BQP are incomparable. What does it mean incomparable? That there exists some task that you can solve in BQP but not in NP, and vice versa. There exists some NP complete task that is not in BQP. Okay, let's say that we want to prove that these containments are false, that there exists some task in one and not in the other. Could we do that? Well, if you think about it a bit, you realize that doing that would, in particular, separate P from P-space, right? So since everything is contained in P-space and everything contains P, it will mean that we found something in P-space that is not in P. And this is a huge open problem in complexity theory that we are seeing very far from solving. And it seems very out of reach in the scale of P versus NP, so we will not solve this problem today. I guess if I would have solved this, I would have a different title for this talk. Okay, so what do? We actually relax this question a bit. So instead of working with this question, we relax it and ask for a separation with respect to an oracle. Okay, so let me explain you what this means. So an oracle is this sort of magical black box. I can ask it a question, okay? And the oracle would answer me within 1 second. Okay, so I give it a very long question, and the oracle say yes or no. Okay, but is it useful? So sometimes the answers of the oracle would be useful to whatever I'm trying to compute, and sometimes it will not be useful. And the idea of an oracle separation is that for some devices, the hints that the oracle offer would be helpful, and it will help us finish the computation very efficiently. But for other devices, the hints that the oracle give are not helping at all, and sort of they are still stuck. So maybe a good illustration for this is a story that I took from Terry Tao's blog. He says, let's say that you want to compare two students. You want to say which student is wiser. And let's call these students P and NP. And you know, both P and NP sits in their office, long hours, and they don't produce any theorems, any results. They don't write any papers. It's hard to tell. So you say, okay, I will give them a computer. And you give them the computer, and after a week, you see, well, NP produced so many papers, and P is still stuck. Okay, so this gives you some evidence about, you know, who is wiser. But you should take it with a grain of salt, because sometimes if I give you one oracle, then you know they are different, and another oracle they will be the same. So you should take this oracle separation with a grain of salt, but we see it as some kind of evidence on the true answer. Okay. So to be more formal, what is this oracle? So it's basically, as I said, it's just this black box, or you can think of it as a function that you give it a Boolean string, and it tells you yes or no. So you give it something of arbitrary length, and it tells you either 0 or 1, yes or no. And you can define, with respect to this oracle A, you can define a whole bunch of complexity classes. So you can define P to the A, NP to the A, PH to the A, BQP to the A, you know, all the classes that I said before. You can add this superscript A. What does it mean? It means that you do the same kind of computation as you've done before, but you can have an additional resource, which is this oracle. So you can ask this oracle questions, okay, and it can help you sometimes. So for example, we said that a language is in P if there exists some Turing machine that runs in polynomial time that can decide whether or not a string is in the language. And we said that the language is in P to the A if the same thing holds, but this Turing machine has also access to an oracle A. It could write a question to the oracle and get the answer within the next time step. Okay, so with respect to oracles, we know many separations. Okay, so we know how to separate P from NP. We know how to separate NP from the polynomial hierarchy. And we know how to separate the polynomial hierarchy from P space. Okay, so these are all seminal and classical results. And there are also results separating between the classical world and the quantum world. So the seminal result of Bennett, Bernstein, Brassard, and Vazirani showed that there exists some oracle such that NP to the A is not in BQP to the A. So there exists some tasks that an NP machine could solve with access to this oracle. But if you have a quantum algorithm, it requires you exponential time. And this is seen as a good evidence of the fact that, you know, quantum algorithm would not be able to solve NP-complete problems. It would still take them exponential time. In fact, the lower bound here on the running time of the quantum algorithm is exactly 2 to the n over 2, which is exactly the running time of Grover search. So it shows that Grover search is optimal for this task. Okay, on the other hand, okay, we are here in QIP, so we want to show that quantum is useful for something. So we want to show, so in this seminal result of Bernstein and Vazirani, they show that there exists some task where a quantum algorithm, okay, there exists some oracle such that BQP to the A is not in BPP to the A. So some tasks that can be performed by a quantum algorithm, but not by a randomized algorithm with access to the same oracle. And this task was called recursive Fourier sampling, and for the same task, you can actually show a stronger result. You can show that this task is not even in MA, which is some kind of generalization of both BPP and NP. And Watrous showed it for a different task. He showed the same separation, but it still remained open since this work in the early 90s, whether or not BQP is inside PH, and maybe this holds even with respect to all oracles. Okay, so there was no oracle separation between BQP and pH. I should say that some results, so if I can simulate one machine in a black box way by another machine, then this implies also the same thing under oracles. So some results hold with respect to all oracles, but some results don't. So we should keep that in mind. So our result is really an oracle separation of BQP and pH. Just to make sure that we're on the same page, I want to formally define pH, or the polynomial hierarchy. So we say that the language L is in pH if there exists a constant K and some polytime computable relation R, such that I can express membership in the language. I can express whether X is in L by this formal expression. There exists some string Y1, such that for all strings Y2, there exists some string Y3, and so on, and I do this alternating quantifier for K steps. And then I take the relation and apply it on X, my input, and all the Yi's. So for example, if I have only one existential quantifier, this gives me the power of NP. I'm checking whether there exists some solution. So I'm checking whether there's a traveling salesman path of a given length. Okay? If I allow only one for all quantifiers, then I check CoNP. I get the power of CoNP, but I can have, let's say, 100 quantifiers. Okay? And I can take them alternating. One example is computing the VC dimension of a set. You can do it in the polynomial hierarchy, but we think that you cannot do it in NP or in CoNP. Okay. So what do we want from this? We want the K to be a constant, and we want the strings to be of polynomial length, right? So our main result is we show that there exists some oracle and a decision problem that BQP to the A can solve, but pH to the A cannot solve. In fact, we can even rule out not only constant many quantifiers, but number of quantifiers that goes with the length of the input, even up to linear. Okay. And I want to give this quote of Lance, who commented on our work. He interpreted it as follows. Even if P were equal to NP, even making that strong assumption, that's not going to be enough to capture quantum computing. So let me explain what does Lance mean. So you could imagine a world where P equals to NP. And in such a world also, the entire polynomial hierarchy collapses to P. So if P equals to NP, then entire pH equals P. Even in such a world, there exists some tasks that a quantum algorithm can do that a classical machine cannot do. So quantum algorithms are capable of doing tasks that are outside NP, outside pH. This is fairly surprising, I would say. Because if you think about it, the famous example that we know, like factoring, is inside NP. Right? And even Lance made it precise, and in an unpublished work, ongoing work that he will publish soon, he's showing that there exists some oracle where P to the A equals NP to the A equals pH to the A, but BQP is not contained in P to the A. Okay. All right, so we talked a lot about oracles, but now I want to switch gears and talk in a different language. So I want to talk in the language of pseudorandomness, and let me introduce this notion in this slide. And you will see how these two languages connect in a slide or two. Okay, so I'm starting on the right-hand side. So here I have a completely random string of coins, okay? So each coin is heads with probability half, tails with probability half, and they are independent of one another. Okay, so this is truly random. On the left-hand side, we have these silver coins. So they are not gold coins. They are not like excellent. Some of them may be a little bit biased. Some of them may have some correlations between them. But still, we say that they are pseudorandom. They look random to the function f that operates on this string. How do I quantify that? I say that the distribution D, and think of D as this distribution of silver coins, is pseudorandom against a class of functions, C, if any function in this class, if any f in C, has similar expectation on this part, on the D distribution, as it has on the U distribution. So I'm thinking of Boolean functions, so this is really asking what is the acceptance probability of the function. Okay, so I'm saying the acceptance probability here would be the same as the acceptance probability here. And maybe I will allow a difference of an epsilon between these two probabilities. Okay, so maybe I will allow a very small epsilon difference. Okay, so what is the connection to the pseudorandom setting? This was established in the work of Scott 9 years ago, and then later extended in the work of Pfefferman et al. So both of them sort of posed this challenge and also gave candidates to this challenge. So they posed the following challenge in pseudorandomness. Can you find a distribution which looks random to AC0 circuits? These are bounded depth circuits, and we will see them in a few slides more formally, but basically circuits of very of constant depth or very shallow depth. On the other hand, the distribution would not look random to a super efficient quantum algorithm that runs in polylog time. Okay? So let's say that you met this challenge and you found distribution with these two properties. It looks random if F was a very shallow circuit. It doesn't look random if F is a super efficient quantum algorithm. Assuming that you solve this problem, you get an oracle separation separating between BQP and pH. Okay, so this may seem a bit mysterious. What is the connection of this circuit and pH? Okay, so this goes back to the early 80s. Basically, you can take any language in pH and translate it into a circuit. So you replace every quantifier with a huge gate. So if you have an existential quantifier, you replace it with a huge OR going over all possibilities. If you have a for all quantifier, you change it with a huge AND going over all possibilities, and you replace the relation with an OR of ANDs. So basically, for any language in pH, there exists some circuit with depth k plus 2, where k is a number of quantifiers, that sort of simulates it. Okay, so this is the connection between the two. Maybe I will show you a little bit of this reduction in a few slides, but let's just, for now, focus on this question. So we are really asking now for a distribution on strings, Boolean strings, that look random to shallow circuits, but doesn't look random to super efficient quantum algorithms. Okay. So I want to state our result in this language. I say that the function f has advantage alpha distinguishing between the distribution d and u, if alpha is the difference between the acceptance probability on f on d and the acceptance probability of f on u. Okay? So recall that pseudorandomness just means that alpha is small. So we present the distribution d such that there exists a super efficient quantum algorithm running in logarithmic time that can distinguish between d and u with advantage at least 1 over log n. Okay, so the difference between the acceptance probabilities would be at least 1 over log. On the other hand, we show that any constant depth circuit of poly size or even quasi-polynomial size, like n to the log n or something bigger than that, can distinguish between the two with advantage at most 1 over square root n, so much, much smaller. So you can see that there is a huge gap between these two results. So this says that the advantage of the quantum device is at least 1 over log, and this is the advantage of the classical circuit is at most 1 over square root. So it's an exponential difference, and you can even make it bigger. So by standard techniques, you can sort of amplify the success of the quantum algorithm by repeating this experiment maybe polylog n times. You can make it arbitrarily close to 1, let's say 1 minus 1 over poly n. Okay, so the quantum algorithm really can tell the difference. He would say here 1 with high probability and here 0 with high probability. Okay. So I will not get into these amplification techniques. I will just present to you these main results and the main ideas that go into the proof here. Okay. But before diving into the ideas of the proof, I would just want to show you the connection again to the oracles. Okay, so we talked about oracles and then we talked about the distribution. So let's connect the dots. So how do you get from this distribution the oracle, and how do you get the language that separates, the computational task that separates between the two? So sort of the language and the oracle would be defined together. So the language would actually really depend on the choice of the oracle that we are doing. And we will do it using the probabilistic method. So for each input length n, small n, okay, I look at capital N to be 2 to the small n, And I need to say how the oracle looks like on strings of length small n. So this is just a truth table, right? So I need to answer just all possible queries of this length. It's just a truth table of length 2 to the n. So I specify it using a string of length capital N. And how do I sample this string? With probability 1/2, I will sample the string according to this distribution D. Let's just give it a name so that it will be easier to remember. So D will be actually for relation. And the other with probability 1/2, I will pick this string according to the uniform distribution. Okay. And then, so this defines the oracle actually. How is the language defined? So I will add the string 1 to the n to the language if and only if the string Sn was sampled according to Dn. Okay, so depending on my choice here, I would add 1 to the n to the language. Okay? And then the claim is that a quantum algorithm can decide whether or not 1 to the n is in L. How can he do that? He would just run the distinguishing algorithm. He has access to the string. He has oracle access to this string. So we just run his algorithm distinguishing between these two distributions. And he can tell in time polylog of capital N, he can tell whether or not we are in this case or in that case. Polylog of capital N is really poly of n, so this would be polynomial time. On the other hand, by the connection of this pH machine to an AC0 circuit, we can show that any pH machine cannot really tell the difference. It should sort of be confused. It cannot really tell if we are in this case or in that case. And then there would be some input length on which this pH machine would make an error. So this is sort of like a diagonalization argument. So any pH machine would make an error at some place. All right, so this is a proof sketch just to connect the dots, but we will focus now on this pseudorandom setting. So we would focus on define this distribution D, the correlation distribution, showing that there exists a quantum algorithm that run in logarithmic time that can distinguish between this distribution and the uniform, and then showing that this distribution is pseudorandom against shallow circuits. And this is actually our main contribution. Both steps 1 and 2 were already given to us by Scott, and there was another candidate by Pfefferman et al., where he also gave some candidate of a distribution and a quantum algorithm and conjecture. In both works, they conjecture that this distribution is pseudorandom against AC0 circuit, but this remained open, and we are able to prove this. Okay, so I lied a bit because we are actually changing, we are tweaking the distribution that Scott proposed a bit. So I will tell you exactly how this distribution looks like. Okay, so we want to sample in the end strings of length capital N. Okay, and capital N was a power of 2. And I will have some parameter epsilon, which would be roughly 1 over log n. But for now, just think of it as a parameter, and by the end, you would understand why I picked it to be 1 over log n. Okay, so I want to define a distribution over Boolean strings, okay? So a discrete distribution. But to do that, I will first define a distribution over the reals. So I will define a multivariate Gaussian distribution that can get real values. And from this Gaussian distribution, I will, in the end, deduce the Boolean distribution, the discrete distribution. Okay, so let's start with the Gaussian. I'm drawing x1 up to xn over 2, IID Gaussians with mean 0 and variance epsilon. So really maybe the simplest Gaussian distribution that you can think of, but that's not the end of it. Then I take this vector of x's and I multiply it with the Hadamard matrix. Okay, so this is well known in quantum computing. The Hadamard matrix is sort of like performing the Fourier transform, right? And that's why the name correlation is sort of like saying that two vectors are correlated after you apply Fourier on one of them. Okay, so that's the idea of the name, but let's see what it actually means. So you take this vector of x's, you multiply it with the Hadamard matrix, and you get a vector y1 up to yn over 2. And basically, the distribution will be just a concatenation of the x part and the y part. Okay. If you do the calculation, you realize that this is actually a multivariate Gaussian distribution defined over n dimensions, where the means are 0. So for each individual coordinate, the mean of this coordinate is 0. And the covariance matrix is specified by this form. So it's epsilon times this block of identity, a block of Hadamard, and a block of identity. So basically, the correlation between the x part and itself, there are no correlations. There are some correlation between the x part and the y part, according to this Hadamard matrix. And what is this Hadamard matrix? So it's this n over 2 by n over 2 matrix, whose ijth entry equals 1 over square root n over 2 times -1 to the inner product of the index I and the index j. So I think of both I and j as like binary representations, take their inner product modulo 2. Okay, so what's important about this Hadamard matrix? Two things. One is that a quantum algorithm can perform this transformation very fast. It can perform it in logarithmic time. The other is that all these entries are small. Okay, so for the lower bound, we will need actually that all these entries are small in absolute value. Okay, so all of them are of the scale of square root n over 2. 1 over square root n over 2. All right, so this gives me a Gaussian distribution. How do I get the discrete distribution from it? Well, the idea is to first sample z according to g. Okay, so this gives me a bunch of real numbers. Then I'm going to truncate these numbers. So if a coordinate is bigger than 1, I make it 1. If it's smaller than -1, I make it -1. If it's in between, I'm not doing anything. I'm keeping it as is. So now you can ask yourself, what would this truncation operation do on this vector of z? And the answer is that with high probability, it will do nothing. And why is that? It's exactly because of the choice of epsilon. Remember that each coordinate individually had mean 0 and variance epsilon. Epsilon was chosen such that with high probability, all the coordinates will be within the interval -1, 1. Right? So we know how Gaussian distribution looks like. We know that if we pick this variance, then the probability to be bigger than 1 is 1 over poly n. So that's why we picked it. And basically, you can sort of ignore this truncation operation. But in order to be formal, we have to say it because for the next bullets. Okay, so after the first bullet, we got a bunch of numbers between -1 and 1. Okay, now all the coordinates are between -1 and 1. And now, how do we translate it into a really Boolean thing? So for Boolean, I want each coordinate to be either +1 or -1. So I'm going to draw for each individual coordinate, I going between 1 and n, I'm going to draw independently a random variable z prime I, which will be a +-1 random variable, and I will pick it such that the expectation of this variable would be exactly the value of zi. So I can think of these zi's as biases of coins, and I will flip coins with these biases. So if z1 was 0, I'm really flipping a random coin. If z1 was 0.99, then I'm picking one with very high probability. Okay, so this is sort of continuous way to transform a real number into discrete distribution. Scott had a different suggestion. He suggested just to take z prime I to be the sign of zi. We don't know how to analyze this suggestion yet. Okay, so it is important for us that if you make a small difference in the value of the zi's, the distribution is very similar. And this is important for the proof that this is pseudo-random against circuits. Okay. So I want to give you a little bit of intuition to how do we get this separation, but just by looking at this distribution. I will hint to the key properties of this distribution that allow for the separation. So as you can see, this distribution is very similar to the uniform distribution. So if I look at only on the left-hand side, the first half of the input bits, they are all independent of one another, and each one is unbiased. So they are really independent bits. Also, it's true for the right-hand side. So all we have is this small correlation between, the xi's and the yj's, right? And this correlation is the order of 1 over square root n. Somehow, miraculously, the quantum algorithm is able to take all these small pairwise correlation and sort of accumulate them together, get a constructive interference, and get a big amplitude in the end. Okay, so you would get an amplitude of roughly epsilon in the end, which is 1 over log. On the other hand, okay, so if I only look at, let's say, just 2 coordinates, like xi and yj, I get an advantage of 1 over square root 10. Basically, our main result on bounded depth circuits, on AC0 circuit, would be that it cannot do much better than that. It cannot amplify correlations. Okay, and this is the important key properties that we are proving, that AC0 circuit cannot amplify this small pairwise correlation, and basically, the advantage that an AC0 circuit would get is something like polylog divided by square root n. So not much better than just looking at 2 variables. All right. So this is the intuition, but let's see the details now. So I will briefly mention the quantum algorithm distinguishing between these 2 distributions. I have here sitting in the audience both Scott and Andres, so it's actually very close together. So this is the algorithm that's suggested by Scott and then refined by Scott and Andres. They gave a low order log n time quantum algorithm. It runs in log time. It actually makes only 1 query to the input, and it can tell the difference between these 2 distributions. So let's see why. So let's think of a fixed input, x, y, and think what is the probability that this algorithm Q accepts this given input. So here I really think of the probability over the, the quantum measurement. So the input is fixed. I'm only looking on the probability over the quantum algorithm. So this probability is equal exactly to 1/2 plus the inner product of hx, where h is this Hadamard matrix, and the vector y divided by n. Okay, so this is what they proved, and we will see some sketch of it in the next slide. Let's see that this is enough for our, this is enough to show that this distinguishes between the 2 distributions. So what is the expected value of this expression over the uniform distribution? When we take the uniform distribution, both x and y as mean 0, and they're independent of one another. So really this inner product, the expected value of this is 0. So we get that the expected value here is 1/2. On the other hand, on the correlation distribution, what do we know? We know that y is actually equal to h of x. So what we get here is 1/2 plus the norm of h of x, or the norm of y. And this is really, or the norm squared, sorry. So this is really epsilon times n. Okay, so all in all, we get 1/2 plus at least some constant times epsilon. Okay. So I just want to say that this algorithm is not too complicated. As I said, it makes only 1 query, so it cannot do a lot. So basically, this is a sketch of how the algorithm looks and how the state looks like. So you start with a superposition over, right? So you have this string that is sampled maybe according to the uniform distribution and maybe according to the correlation distribution. So you start with a superposition over all bit location of this string. So you go over all possible i's between 1 and n. So I'm splitting it into the i's that are in the left part of the string and the i's that are in the right part of the string. And then you query. When you query, you multiply the phase by the value of xi in this part and the value of yi in this part. Okay, so this is just querying in superposition the string. And then you apply the Hadamard transform, but only on the left-hand part of this state. Okay, you can do it in logarithmic time. And then you measure in the ±1 basis. And you can check and do the calculation and see that the probability that you would accept is exactly 1/2 plus 1 over n times this inner product, okay, between h, x, and y. Okay. So really, I'm not sure it's easy to get a good intuition from this slide, but maybe what I wanted to convey is that the algorithm is not super complicated, and also the analysis of it is something that you can do within a few lines of calculations. All right. And the true power here of the quantum algorithm comes from the fact that we can perform this Hadamard transformation in logarithmic time. Okay. So our main result, and this is what I want to focus on today in more detail, is the fact that this distribution is pseudorandom against AC0 circuits. So let's just, to make sure that we're on the same page, let's see how does this AC0 circuit looks like. So these are bounded depth circuits. They are composed of AND gates and OR gates. Each one may have many inputs feeding them, unbounded fan-in. And I have on the leaves variables or their negations. Okay? And the two parameters that I would keep in mind is S, the size of the circuit or the number of gates that I see here, and D, which will be the depth or the number of layers of gates here. Here the depth would be 3. And the parameters that I'm focusing on is when the depth is a constant and the size is n to the polylog n. Why do you ask? Why do I care about these parameters in particular? This is what you would get if you translate a language in pH to a circuit. Okay? All right, so we know quite a lot about this circuit, about this AC0 circuit. We know how to prove lower bounds. We know how to show that some distribution is pseudo-random against them. So let me tell you a little bit about the history. So this was first studied by Sachs, Sipser, and then Aita, Yao, and Hastad. They were motivated by these oracle separations. And they showed that the parity function cannot be computed in this model. And in fact, it requires exponential size for depth D. Okay, so it cannot be computed in this model with, polynomial size or quasi-polynomial size. It even requires exponential size. Okay, there are by now many proofs of this fact. I want to mention one of them, one of the proof techniques. So this proof technique uses Fourier analysis. You can show, and this is based on the work of Hassad, Linian, Mansour, and Nissan, show that any bounded depth circuit, any AC0 circuit, can be well approximated by low degree polynomials. So you look at this circuit, which is a Boolean function, and you can find a low degree polynomial over the reals that gets the answer correct up to a small error. And the small error is with respect to L2 norm. Okay? On the other hand, if you want to approximate parity even a little bit, you need degree n. Okay, so this will be of degree polylog, and this requires degree n. So this shows you that parity is not an AC0 circuit. In fact, it also shows that parity cannot be even approximated by such circuits. Okay, so can we apply this proof technique to our separation? And you run into some obstacles trying to do that. Well, the first thing is that a quantum algorithm, super fast quantum algorithm that runs in logarithmic time cannot solve parity. But the problem is bigger than that, because the seminal result of Bills et al. Shows that anything that a quantum algorithm can do, in logarithmic time, is also, or actually in logarithmic queries, is also well approximated by low degree polynomials. So you can write the acceptance probability of the quantum algorithm as a low degree polynomial. So this sort of tells us, this notion of low degree polynomials is the wrong notion to distinguish between these two devices. Both AC0 circuits and super fast quantum algorithms are well approximated by low degree polynomials, so maybe that's the wrong approach. Nevertheless, we were still persistent, and one reason for our optimism was the fact that we realized that, both have low degree approximation, but they are of very different flavor. On one hand, some tasks that BQ log times, that quantum logarithmic time can solve, requires to have very dense low degree approximations. On the other hand, AC0 circuits always have sparse low degree approximations. And let me show you that already we saw this in the algorithm or the analysis of the algorithm of Scott and Andres, right? We said that the probability of acceptance of their algorithm is 1/2 plus the inner product of h, x, and y divided by n. Okay, so I opened this up, and you can see that this is really a low degree polynomial in the input variables, right? So the input variables are the xi's, the xj's and the yi's. And this is a polynomial of degree 2 in these variables. This should not be surprising because the query was actually 1, so that's why we got degree 2 by the result of Beals et al. But if you look at this polynomial, it's really dense. It's of degree 2, but it has order n squared coefficient, and it's not like you can sort of like erase half of them and hope for the best. It would just not be a good approximation. So it's really dense. On the other hand, in a result that I showed 5 years ago, I showed that you can take the number of monomials in the approximation to grow something like polylog raised to the degree, raised to k. So if you look at how many monomials you have of degree 2, this will be polylog squared. Okay, so very much smaller than order n squared. Okay, to be more precise, what I showed, which implies this, is that if you look at the sum of absolute values of Fourier coefficients of sets of size k, and if you are not familiar with that, I will show it in the next slide, then this is at most polylog n to the k. Okay, and this is what I call this non-amplifying property of shallow circuits. And I need to explain why, but okay. So the first attempt would be just to take this, this result and try to show using this result that the correlation distribution is pseudorandom. Okay, so the first attempt, and by the name you can guess how it will end up with, is to use a Fourier analytical approach. Okay, so I'm using the fact that any Boolean function, any function mapping, strings of length n to plus minus 1, can be uniquely represented as a multilinear polynomial. And this is called the Fourier expansion. So I write f of x as the sum over all subsets of the coordinates between 1 and n, have a real valued coefficient for each subset, times the monomial. Okay, the monomial is just a product of xi, where I is in this set. Okay, so there are a lot of beautiful properties of this representation, of this Fourier expansion. But the one thing that I want to emphasize today is that it gives us a very natural way to extend a Boolean function, which is a discrete object, into a continuous object, right? Because we write this over the reals. So this is really a polynomial over the reals. And now we can think of it, how it behaves over real entries. Okay, so we know that if we give this polynomial, a vector where all the coordinates are plus minus 1, we would get exactly the values that the function gives us. But what would happen if I give it 0.7 or minus 1.2? Okay, so it still would give me something, but how should I interpret that? Okay, so recall that our goal was to show that the expectation of f under the correlation distribution is similar to the expectation of f under the uniform distribution. And I claim two things. That the expectation under this correlation, this discrete correlation distribution, is very similar to the expectation under the Gaussian distribution. And also that the expectation under the uniform distribution is exactly the value of this multilinear extension on the all zeros input. Okay, so you gotta trust me on that, but basically if you want to convince yourself, you should think of f as just, a single monomial, just a product of some xi's, check that it actually works, and then use linearity of expectation to show it for general functions. Okay. And here it's really crucial that we are using our definition of correlation, so this would not hold with respect to the original definition of Scott. Okay, so this allows us to go from, the discrete setting into the continuous setting. So now we can replace this thing with the expectation over the Gaussian distribution. And here, in order to even interpret this f of z, we need to think of the multilinear extension or the Fourier expansion. And I replace this by the value of f on the all zeros vector. So that's what I want to show now. Okay, and you can do the most naive thing and try to bound this using the Fourier expansion term by term. Okay, so just to show that, the contribution of each term in this expansion is small. So let's write it up. So this actually only gives me the empty coefficient, the Fourier coefficient of the empty set. And this cancels out with the the coefficient of this expansion. So really what we are left with is the sum over all non-empty sets. We have this coefficient f hat of s, which is just a real number, times the expectation of this monomial evaluated, okay, when I take the expectation over the Gaussian distribution. Okay, so this is what I want to bound now. I want to show that this quantity is small. All right, so, you know, this is a Gaussian distribution with mean 0. So this means that the expectation of Z1 is 0, and Z7 is 0, and Z1, Z3, Z7 is 0. Okay, so we know that the expectation of all the odd moments are 0 because this is a symmetric distribution. So we can sort of like group this coefficient according to their degree, and we are left with only the even degrees. To analyze the even degrees, I can use Isserlis theorem that tells me how does even moments of a Gaussian behaves with respect to the covariance metrics. And I get that the degree 2L moments are at most epsilon L over square root 10 raised to the power L. This requires some calculation, but this is what you would get. And now we're using these results that I mentioned. So now we are looking at the sum of coefficient of sets of size 2L in absolute values. And we know that we have that this is bounded by at most polylog n raised to the 2L. And let's see what we got. Let's see if what we got is good or not. So if we look at L equals 1, we get something like polylog divided by square root n. This is great. L equals 2, we get something even smaller than that. So on and so forth. So the first L's look very promising. But then we reach L equals something like square root n. And this becomes bigger than 1. Okay, and then we really got a problem. Because we bound it by something that is bigger than 1, this is meaningless. Okay, so what we got is that the contribution of the first term is what we expected, but we cannot control the contribution of the high degree terms. And we were stuck on this for maybe 4 years. We tried very different approaches for that, to change the distribution, to change the approximating polynomials. All these attempts failed, but then we realized that we don't need to change anything. We just need to think about it a little bit differently. Okay, so the second attempt would be the random walk approach. And here I will want to think of this Gaussian distribution differently. I want to make a thought experiment. So instead of sampling the Gaussian distribution at once, I want to look at it as a result of a random walk, making a lot of tiny steps. So how do I do that? I will take t to be really huge, and I will pick z1 up to zt according to the Gaussian distribution. And then I will, so these are just vectors. Then I sum these vectors, and I divide by square root t. When you take the sum of independent Gaussian, you get the Gaussian, and you know the mean is the sum of the means, the variance is the sum of the variances. So actually, you would get exactly the same distribution. It's just a different way of looking at the distribution. And if you take t to the limit to infinity, this gives you a Brownian motion, which is pictured here. So you start at the origin, and you move in a Brownian motion for some time until you stop. And the point where you stop is distributed according to a Gaussian distribution. Okay, so what does this offer us? It offers us to analyze this Gaussian distribution as a result of a continuous process, making a lot of tiny steps. Okay, so what we will do is we will apply a hybrid argument. We would show that in each tiny step, we are not changing the value of the function by much. Okay, so we have h0, the first hybrid, will be just the origin. And for I between 1 and t, hi will be the sum of the first z1 up to zi divided by square root t. Okay, and I know that ht is distributed according to the Gaussian distribution. So really, I want to show that the expected value of the I plus 1 hybrid is very similar to the hive hybrid. Okay, if I'm showing that, then I can apply, you know, triangle inequality and show that the expected value of h0 is very similar to the expected value of ht, and this is exactly what I want. Okay. You can take t to infinity, and this will give you a Brownian motion. This is actually possible by a follow-up work. We took t to be a big number, big finite number that is polynomial in n. This was good enough for us. So I want to give you some taste of how the proof works. So to analyze the first step, we would take the exactly same approach that we did before, the simple Fourier analysis, but this time it would work. This time, because we shrunk the vector, we will kill the high degree terms, and only the low degree terms would matter. In fact, we can approximate the function locally. Since these steps are so tiny, we can approximate it locally by a quadratic polynomial, and we know that this quadratic polynomial is sparse. And then we will show that the ith step, is very similar to the first step by a reduction of CHHL, Shetopadi, Khatami, Husseini, and Lovett. And this uses the fact that this class of function is closed under fixing some of the input bits. So if we fix some of the input bits to zeros or ones, we are still in the class of circuits. Okay, so let me, so this was a high-level idea of the proof, and let me recap now. So we defined the distribution D, which was a discrete distribution, based on a Gaussian distribution G. We briefly mentioned why this distribution is not pseudorandom against very efficient quantum algorithms. This was done by Aronson and Ambanis. And then our main contribution was to show that this distribution is pseudorandom against AC0 circuits. Here we analyze it as the value of the function on a Gaussian and the value on the all zeros vector. So we use the fact that the Fourier expansion moves us from the discrete setting to the Gaussian setting. And to analyze the Gaussian distribution, we thought of it as the result of a Brownian motion or a random walk. We analyzed the first step using the fact that AC0 circuits are approximated by low-degree polynomials that are sparse. And this is the important fact, that they are sparse. And then we use the fact that, the ith step is very similar to the first step using this result. Okay. So that finished up the proof sketch. I want to mention one open problem that I'm interested in. So you can try to take this separation and get a better separation to show that actually this correlation cannot be even computed by a class of circuits that have OR gates, AND gates, and parity gates. And the only missing piece here is a Fourier bound. So you just need to show that for all function within this class of circuit, if you look at the sum of Fourier coefficients of sets of size 2, this is at most square root n over polylog n. We know a bound of square root n times polylog n. So we are really polylog apart from what we need. But we actually suspect that the right answer is much smaller than that. So we need this, but we actually conjecture that this is the right answer, polylog. And if this is true, then we would get a PRG. So basically we can sort of de-randomize this correlation distribution and we can sample something with similar properties using a few random bits such that it still fools this class of circuits. And if this conjecture is true, this would imply maybe the first interesting PRG for this class of circuit, AC0 with parity gates. And this PRG would be with polylogarithmic seed length, and the current best is only linear seed length. So this would be an exponential improvement. And this is really a result that is motivated in the complexity theory and in pseudorandomness. Okay, so let me finish with that, and thank you very much.
So I guess what I'm confused about is how does a proof, an oracle separation, why is it not a conclusive proof? Like if there's an oracle separation that P does not equal NP, why is that not proof that P does not equal NP?
Okay, so the question is why does an oracle separation, let's say that P to the A is not equal to NP to the A, why does it not imply that P is not equal to NP? Okay, so there are proofs of this sort that actually are not true in the real world. So for example, IP equals P space, but there exists some oracle such that IP to the A is not equal to P space to the A. So that's why I said you should take it with a grain of salt. Sometimes giving this extra resource really changes the game. What it actually means is any proof of the, the other direction, proving that P equals to NP, would need to have some techniques that do not relativize, that do not work with respect to oracles. And most of the techniques that we know relativize. So that's what it tells you.
Other questions?
Yeah, so as I'm sure you know, there's also the stricter standard of Aronson and Vigderson of not just any type of oracle separation, but an algebraizing separation. And then their definition is a bit messy, but although it's certainly valid, but then there's this recent slight simplification where you can have one self-algebraizing oracle as well. Do you expect this type of oracle, or do you expect this to be within reach for what you are doing?
That's an excellent question, but I haven't thought about it, so I cannot tell you too much about it. But yeah, maybe it's good to take it offline and maybe discuss it offline. But I haven't thought about it, but it's an excellent question. Thanks.
Hello. I guess you stated that you also get a separation for pH to the A, where, or maybe not pH to the A, but if you take the number of quantifiers that it's not only constant, but also increases with n.
Yeah.
How do I see that from your proof?
Right. So basically, when I said, this IC0 circuit, I said they have this polylog. If I took the number of the sum of absolute values of sets of size k is polylog raised to the power k. This polylog really depends on the parameters of the circuit. So it's something like log the size raised to the depth. Okay, and it suffices for us for this log s to the d to be smaller than square root n. So as long as this happens, we prove a result. So this means that you can take even d to be non-constant. Okay.
Thanks.
It basically gives the same result as you would get for parity. So same lower bounds that you would get for parity function.
Thank you.
You have to hold the mic.
Is there some complexity class between pH and P space which you want to separate? I mean,
I guess that's the ones that correspond to this AC0 circuit with parity gates. It is not so well known, but at least in the circuit world, it is well known.
thank you.
So in the definition of correlation, we use this Hadamard matrix, but it sounds from your proof that any unitary that just all the entries were like 1 over root n in absolute magnitude would work. So we could use different unitaries, different quantum circuits that would work.
Yeah, that sounds correct. Yeah, we had this exchange with Scott, and I think we are convinced that it's correct, but we haven't written it up. So yeah. So it seems that it's not. For example, in the Pfefferman et al. Candidate, it was a sort of different metrics, not necessarily the Hadamard matrix. Yeah, that the entries are small, and that a quantum algorithm can do that. Yeah.
Okay, let's thank the speaker again.
Thank you.